Institute. David, I first got to know as a colleague PhD student at that other institution south of here.
When we got thrown out of class, we got thrown out of class together at the same time.
Where we got thrown out of class together and made people cry and these sorts of things. So since then, David has done a whole variety of different things in the education world, from being a teacher to being a school administrator to pursuing a research agenda that's incorporated everything from looking at student affect and motivation in the sciences to looking at what we're looking at today, different ways of thinking about and teaching students the concept of energy process. David is a dedicated scientist and brings a unique perspective that sometimes challenges our American sensibilities, which is a good thing. And so we hope that you will enjoy him doing that today.
I wasn't kidding, by the way. One of the very first classes we had together, Betsy Davis decided, in order to keep us silent, that everybody got 3 pieces of paper. And every time you said something, you have to give them a piece of paper. And who were the first 2 people who ran out of pieces of paper? Anyways, I'm really glad to be here. It brings always back flashbacks to about 16 years ago when I gave a job talk, standing right here. Anyways, what we're going to talk about today, we're going to talk about energy instruction at middle school. The people, it is an NSF-funded project. Here are the people who contributed at one stage or other to the project. There were 4 PIs, Joe, which is the reason I'm talking here right now, myself, Knut Neumann and Jeff Nordin, who were at IPN in Germany, and lots of postdocs. I listed them alphabetically. First the MSU postdocs, then the IPN postdocs, and then the Israeli, he's not a postdoc actually. But those are the people, and without them, none of this could happen. Plus, thank you very much, Melanie, who's sitting here, who's on our advisory board, and gave really, really good feedback throughout, showing us everything that we were doing wrong. So, first of all, imagine in your mind, okay? Imagine a giraffe. I guess most of you thought something like this. Now imagine a zebra. And probably most of you ended up with something like this. Now I want you to imagine energy. Faces of most people, after they've learned about energy, be they adult or children, is something like this. Okay, energy is one of those topics that research shows that people, even though they've learned about energy from elementary school through to high school, they still struggle to use key energy ideas, such as transformation, transfer, potential energy. These are words that they know how to use, but they don't understand really what they mean. And the idea of conservation, which is really the reason why energy is such an important idea, is totally not part of the discourse when people try to use energy. And because of the first ideas, they don't use energy to make sense of phenomena. Typically, when you give a person a phenomenon, they ask them to make sense of it, they will fall back upon forces and all kinds of other things, anything but energy. So we're doing something wrong with energy. And lots of researchers, just a couple of them are listed below, have questioned the conceptual foundations of the way we teach energy, whether they might be at fault for the way kids and adults are thinking about energy. So it's not just instruction itself is bad, but the actual ideas that we're trying to get across to kids and the way we're doing them, okay, are fundamentally wrong. Following up on these studies, the NGSSS and the framework recommended teaching about energy in a different manner. So first of all, they emphasize the fact that energy is a unitary quantity. There's only one thing, energy. Although we talk about kinetic energy and gravitational energy and elastic energy, it's really only one thing, energy. Okay? That energy is equally useful across disciplines, that energy can be stored in fields. This is a biggie. This is new. Okay, something has not been on the radar screen for most people until now. Okay, and that energy is best understood at the microscopic level. So, we decided to go ahead and try and develop a new approach to teaching energy. Okay, following the recommendations of NGSS, staying away from a lot of what other people have been done. And very briefly, to compare the two approaches, we're going to go a lot more into detail, but very briefly, in the traditional way that energy has been taught, there are energy forms. As I mentioned, different types of energy. In the new approach, we only have energy. We don't have this additional word connected to it. We do not have forms of energy. In the traditional forms-based approach, you have two mechanisms involved. Hi, Andy. You have both transformation, in which energy changes from one form to another, and you have transfer, in which energy moves from one body to another. In the new approach, we have only one mechanism. We have transfer. We do not have transformation. It doesn't make sense to have transformation if you don't have forms. Okay? In the old system, they usually talk about objects and objects energy. In the new approach, we talk about systems. Okay? Having energy. In the old approach, fields was not part of the vocabulary at all. And here, in the new approach, it plays a central role. Now, let's think, if you take any phenomena in the traditional way of thinking about it, what would you have to do? The first thing, you have to look and try and identify what forms of energy are involved in the phenomena. So, for example, when you have a pendulum swinging back and forth, you say, okay, we have gravitational energy because it's changing height. We have kinetic energy because speed is changing. We have thermal energy because it's losing energy to the surroundings, and so on. So you start identifying which types of energy involved, and then from there you start figuring out which is getting transformed to which at what part, and if there's more than one object, if there's transfer going on at the same time. So that is the process of thinking about a problem through the traditional way of thinking about energy. And a representation that looks at that is this one. It's drawn from a curriculum called IQuest, which uses the old approach. So we have a pendulum swinging back and forth. We photograph it at a couple of separate locations. And in each location, there's a pie chart that shows how the different types of energy are distributed between them. So for instance, over here at the upper pole, there's only gravitational energy. As it starts falling down, halfway down, we have half and half about gravitational potential. And a little bit has already become thermal because it's friction with the air, or perhaps also friction at the hinge. When you go down, no gravitational, all kinetic, okay, a bit more thermal. And again, as you're going back up, the kinetic starts to be retransformed into gravitational. Each time, a bit of it gets moved over to thermal. So this is a typical way of thinking about energy from the traditional approach. Energy conservation is implied here because the pie chart has a fixed size. Okay, so this is the amount of energy you have in this approach. Problems with this is that you have to start talking about reference heights. Why is there not, if the reference height was lower down or higher up, would there still be gravitational energy at the bottom or not? What happens if you have an open system, which energy is entering and leaving? How would you deal with that? So this works in many, many, many phenomena, but it has its issues. Another representation would be in the instance of transfer. Let's say two colliding balls, billiard balls, okay? So one has kinetic energy, it strikes the other, it transfers its kinetic energy to the other ball, and it moves on. And here again, energy conservation is applied because energy is moving from one object to another. It's not going anyplace else. The new approach, which I'm calling now the transfer-only approach, okay, can be summarized in this sentence. In every phenomenon, energy is transferred between interacting systems such that each undergoes a process that increases or decreases its energy. And that can be shown in this representation, where the colors match what's happening in the sentence above. So we have systems. In this case, we have two systems, red boxes, and each system is named inside there. We have energy being transferred between the systems, which is our blue arrow, energy going from one system to another, and we have processes that are going inside each system as energy is transferred to or from it, which is the yellow stuff. Now, if you look at the pendulum, how would the pendulum look in this representation? Okay, we have three systems. We have the pendulum, or actually the bob itself. We have the gravitational field. This is something new that wasn't around before. And we have the surrounding air. As the pendulum swings, energy is transferred from the field to the pendulum and back and forth from the pendulum to the field. Each time some energy is transferred, some is also transferred, is lost to the surroundings. So we have only energy here. We don't have types of energy. Okay? What we talked about before, what we would call before as gravitational energy, is actually energy of the gravitational field. If you talked about elastic energy, it was energy, okay, of the field between the atoms inside the elastic object. So we don't have to talk here about types of energy. We just talk about energy and the system in which that energy is situated. What we also have here is, the small thing is the processes that each system undergoes. So over here, the field, okay? The field is actually changing its shape, but that's something that we cannot see. And one of the kids learned is that there are proxies for the changing the field. They do that especially with the magnetic field, where you can actually see the field changing shape as things get closer or further apart. So here, the proxy for the change in the field, okay, is the pendulum getting higher or lower. The process that the pendulum undergoes is getting faster or slower. The process that the surrounding air undergoes is that it's getting warmer. Now, again, comparing the two approaches, the traditional approach, the forms-based approach, I think it deals a lot with naming, just giving names to things, but it doesn't really give you a sense of what's going on. Saying that kinetic energy is transferred into gravitational energy, it in itself does not carry anything deep understanding what's going on. So, for example, when we have something, a candle burning, when two substances undergo a chemical reaction and the temperature increases, energy is transformed from chemical, which is a potential type of energy, to thermal energy. That's what you would say about it from the old perspective. The chemical energy has been transformed into thermal energy. The new approach would say, when atoms rearrange during a chemical reaction, energy is transferred to or from the fields. Okay? Okay? Sentence is wrong. Okay? Energy is transferred to or from the fields to the atoms. The sentence is missing, I'm sorry. Okay? Temperature increase or decrease means that energy is being transferred from or to the field and to and from the atoms. So because we're talking about the field, we're talking about processes, we're talking about interactions, we have to describe this, we have to go in microscopic, as the NGSS recommended. Another example, why we think the new approach is more generative, provides a more generative lens. In the forms-based approach, when we have a solar cooker heating up something, we would say light energy is converted into the thermal energy of the food being cooked. In this approach, we would say energy is transferred from the sun via light to the food as its temperature increases. Okay? Now, because we say here that energy is being transferred from the sun, this is something about the sun. It means that the sun must be undergoing a process as well, meaning just by the fact that we're cooking something, we know that the sun is decreasing in energy. This is something which is not clear in this perspective. So we think that this perspective is more generative unless it forces you also to think about systems that sometimes you might not be forefronting. We think the new approach will help bridge between the disciplines. The language used when talking about energy in the different disciplines is very different. Physicists talk about forms of energy, they talk a lot about conservation. Biologists don't talk about conservation. They don't talk about forms of energy. Okay? They have ecosystems, okay, in which energy is being transferred between different levels. They have cells in which you have coins of ATP, which is available energy. Okay? They don't really care as much about forms of energy, okay, and conservation and so on. But when we look at the NGSS, what they say about the different disciplines, it fits a bit better with the new perspective here as well. All Earth processes, under Earth science, all Earth processes are the result of energy flowing and matter cycling within and among Earth systems. So the key idea about energy is flow. Energy flow is energy transfer. Under life science, ecosystems are sustained by the continuous flow of energy originating primarily from the sun. So once again, we think the idea of transfer, okay, if that becomes the center of our thinking about energy rather than transformation, okay, it will help kids bridge between the different disciplines better. That's our hope. Now, the unit itself is comprised of 5 learning sets. I want to briefly explain to you how the unit is set up and then go over to the study that we did. Okay? In the first learning set, okay, excuse me, we have 3 main phenomena that we focus on. One is the Rube Goldberg's machine. Basically, we have a video of a Rube Goldberg machine that we analyze what's going on inside there. We have a radiometer, and we have a HEROES engine. Does everybody know what these are? Radiometer, you shine a flashlight on something and it starts spinning. Okay, HEROES engine is basically a can with some water inside it, liquid, and you have made holes, pinpoint holes. You heat it, the water boils, steam comes out, and because the holes are at an angle, it starts spinning. Okay, Hero was a guy who lived back in ancient Greece, who first developed the device. So these would be the representations that we use for the radiometer and for HEROES engine. The radiometer, we have a flashlight. The process it's undergoing is glowing. We have light going across. The radiometer, the process it's undergoing is spinning. For HEROES engine, we have a candle which is burning. Okay, heat is being transferred to the can, which begins spinning. What are the key ideas that we're trying to help kids learn in the first learning set? First, when an object starts moving, energy is transferred to it. So over here, we are still not talking about energy, but we're giving examples of things that can be transferred and that can make things happen when they get transferred. In the next learning set, we will start calling them energy. When an object heats up, energy is transferred to it. Energy can be transferred by heat or light. Those are the ideas we're setting over here. Regarding systems, objects can work together to accomplish a task. We can think of a device as one system or smaller subsystems working together. So that's another big idea that we have over here. Okay, not only do we have, as we said, transfer, energy is a single idea. Okay, in fields, we haven't mentioned fields yet here, but we also have systems. We focus here heavily on systems, which in traditional energy education has not been as much of a focus. In the second learning set, 3 phenomena again, hot and cold knives. What are hot and cold knives? We simply take 2 knives, we stick one in cold water, we stick one in hot water, we have a thermometer connected to each of them, we take them out, we put them in contact with each other, and we wrap them up in a towel. And we see how the thermometer's reading change over time. So basically, heat is being transferred from the hot to the cold one. So that's the first one. And this would be, okay, the model that represents that. We have the hot knife, its temperature is decreasing. We have the cold knife, its temperature is increasing. Notice at this stage already we stopped writing what's on top there. That's not important. It's energy that's being transferred. Key ideas over here. Temperature increases as random particle motion increases. We have online simulations developed by Concord Consortium that we're using over here to see what's going on inside there. Energy transferred to or from a system must come from another system. When one system's energy increases, there must be another interacting system which energy decreases. It doesn't come from nowhere. And we can think of as an object as a system of particles. So again, we're focusing on systems, not on objects. So even though we have a single object here, a knife, for us that object, that becomes a system made of many, many subsystems, which are the particles inside there. Third learning set focuses on the idea of fields. We our key phenomena are repelling magnets, pendulum, and a bouncing ball. This would be an example of a model. It's the same as the model I showed you before, except without the dissipation going down, because we're still not talking about dissipation at this state. So it's exactly the same as what I showed you before. Okay? The key ideas are energy transferred to a system must come from another. We mentioned that before, but we're re-emphasizing it over here. A system can be made of a collection of objects and fields. Okay? And focusing specifically on fields, objects can push or pull at a distance via fields. Energy is transferred to or from a field between objects when the distance between them changes. This is one of our biggest concerns in the units, okay? Although we felt the whole approach was simpler than the other approach because we were only talking about one type of energy rather than many types of energy. We're only talking about one mechanism, transfer, rather than two different types of mechanisms, transformation and transfer. Here we're introducing a new abstract idea which is typically not part of the play of the game, and that is fields. And we were very concerned. Our biggest concern probably was how old kids were able to deal with fields. As I said, we introduced fields by starting off with magnetic fields, where we had, after they had learned this and pretty much accepted it, we gave them a situation where we had two magnetic carts close to each other with repelling magnets on them, and we let go, and they start moving away. Now, because the speed of each one increased, that means energy was transferred to each one of them. But we know that energy transferred to a system must come from another. So the question is, where is that system? What is that system that energy is coming from? And that's how we used the idea to get into the field. We did the same thing, but then we had magnetic, how do you call it? Sheets that can map the field, that you put them above it, and as they move apart, you can actually see the field changing. And we had all kinds of other activities with iron filings and so on. So the kids, what they learned about fields, they didn't learn any of the mathematical properties, which is the way fields have traditionally been introduced as a force to the unit of something, as a mathematical property, that we go that way because it helps us use Gauss's law or something like that. So it's typically been introduced as a mathematical property. We didn't do that at all. For us, fields are as real as objects. You just can't see them all the time, but if you have the proper equipment, you can see them. They're there, and they are a system just like anything else. As I said, we were really concerned that that would be a struggling point for the kids. And I'm jumping to the end. Surprisingly, it was not a difficult point up to a certain point. As long as we dealt with macroscopic fields, no problem. Absolutely no problem. The ones we started getting into the fields between, at the atomic level, this became an issue. And I'm not sure yet whether the fields was the problem or simply the ability to envision the microscopic world is the problem. But that's basically where we ran up against the wall. Fourth learning set. Our phenomena, we have bounce, no bounce balls. These are balls that look the same. One bounces, the other one just hits the floor and stays there. We had sliding down a ramp versus rolling down a ramp. We had a thermal camera, and we had a battery-powered pendulum with no battery inside it. Okay. Now, the first two, we used the thermal camera to look at what's going on, and when one ball bounces and the other one doesn't, when you use a thermal camera to look at the floor, one leaves a bright red spot. The other one leaves very little. You don't see that it's been there, okay? And this is looking at temperature, so the thing must have heated up. Where did that temperature come from? So that's what they do. When you slide and roll down a ramp, when it's a ramp that on purpose is not very smooth, okay? It does slide down, but it heats up, and you lose it in your camera. You can see, okay, the trail left by the object on it. But on the other hand, when it rolls down, nothing to see behind it. The battery power pendulum was used over here to describe this situation with dissipation, we on purpose use not just a regular pendulum, we also have regular pendulums, but a battery powered one without a battery, because in the next learning set, we want to use the same thing with a battery. Okay, so we on purpose chose to use a battery powered pendulum without a battery in this case. The key ideas over here were that energy tends to spread out. A device with only energy transfers out of it will eventually cease to function. And it is often useful to distinguish between the system of interest and the surroundings. Last learning set is again, it's the same battery powered pendulum, but now we have a battery that inputs energy into the system. The key phenomena, we had several different exothermic reactions. We did not go into endothermic reactions. Okay, we had them build a battery, an aluminum air battery, and power a small electric fan using the battery, and we had battery powered pendulum. And the big idea introduced over here is that systems and devices can keep going if energy transfers out of the system are balanced by energy transfers into it. The entire unit was structured around project-based pedagogy. I assume everybody here knows this. I don't want to spend time on it. This is not the point of the talk. Okay? Does anybody here not know what project-based pedagogy is? Good. Questions until now? Yes?
I wanted to know how you bridge the gap between the going quantitatively, because quantitatively you do quantify thermal energy or kinetic energy or elastic energy with different equations. So how you bridge this gap eventually?
That's a great question. That's a high school question. According to NGSS, energy at middle school is supposed to be dealt quantitatively. So we didn't have to, in this project, deal with that. Yes, we do have plans, and actually, a month ago, we submitted a new proposal to NSF to try and take this to high school, and to show how could this be done quantitative. Okay, so I don't want to go, we can talk about that afterwards, but it's not really part of this project because we did not deal with quantitative things over here. But you do point out, we do mention the words kinetic energy and potential. We do, because those are the words kids will meet elsewhere. That's the vocabulary that's out there. And you wanted kids to be able to understand things that they were reading. So when we talked about gravitational energy, this was taught to them as shorthand for a process that involves changes to the gravitational field. So when you talk about gravitational, you know gravitational field is transferring energy to or from it. When you hear, okay, some kinetic energy, okay, energy involved with speed. Energy is being transferred to or from the system, and it's changing its speed. So we did not spend a lot of time in that. I cannot say they understand that, because that's not something that we looked at in our assessments, whether they understand these terms. We did introduce it to them because we felt we would be leaving them missing something that's important in today's, the way that energy is typically talked about today. Okay, so it was not left completely off the table, but I'm not sure how well we actually dealt with that. The study, we had several studies. Yeah, Andy.
Just, maybe this is a question for later, but so the phenomena you're using are mostly phenomena that do not involve chemical change and do not involve living systems. And at the same time, in the middle school curriculum, there's content about energy and living systems. So do you think of this as a prerequisite to talking about energy and living systems, or do you think in terms of there also being another approach that's needed to deal with living systems energy at the middle school level?
That's a wonderful question. It's a question we struggled with a lot. Okay, this unit was designed as a replacement unit for the energy unit in IQUIST. So the other aspects of energy are being dealt with in other units in IQUIST. They are not using the formalism that we taught here, but they are being dealt with already. So we have photosynthesis and body systems and earth, so the stuff was inside there, okay? We began the unit by dealing also with chemical phenomena and with biological phenomena. And as time went by, okay, we realized that the scale of what we had was too big. It was simply too much. And we kept deciding, okay, where are we going to chop? Where are we going to chop? Where are we going to chop? Everybody on the team was either a physicist or a chemist. Okay, so it's clear what's left over. So I'm not at all trying to say that this is an ideal solution. Not at all. I cannot vouch that this works as well in the other disciplines. My intuition, I don't know if you were with the slide book, is that it will work better because the vocabulary is a bit more similar, okay, than the traditional vocabulary. So my sense is that we are setting up kids a little bit better. But again, that's just intuition, and my intuition has often been proven wrong. Okay, so it's an empirical question. That's one of the things we want to do when we take it to high school also. That's exactly one of the points. Not only going quantitative, but also looking at in other disciplinary contexts, how well it works across there. So, one of the studies we did, the question driving the study was, how do two different approaches to teaching energy in middle schools, one a forms-based approach and the other a transfer-only approach, support the development of students' NGSS knowledge in use? When knowledge in use, term coined by Pellegrino and Hilton, it's basically their ability to use their three-dimensional knowledge to make sense of actual phenomena. How did we do this? We worked only in schools that adopted IQUIST. And the reason we did that, because it meant that all the kids came into the study with similar middle school experiences. This is a unit that was taught in 7th grade, in the middle of 7th grade. So the kids already had a year and a half of IQUIST beforehand. So we knew what they had before. We knew what the experience they had, what the phenomena they had, what language they were talking about beforehand. So it was easier to design this as a replacement unit that would plug in reasonably well to what they had beforehand and would also allow them to continue on afterwards. So as I said, the new unit was a replacement unit for the IQUIST energy unit. All students began with similar middle school experiences. We administered 2 tests, a pre-test and a post-test, that were NGSS aligned, and I said each question focused on a real phenomena. The kids had to make sense of phenomena. They had to engage in practices, draw upon DCIs, cross-cutting concepts. The 2 tests were similar. They had several overlapping items, but they were not identical. We had additional measures we did, but I'm not mentioning here because they're not necessary for this particular study. A subset of the students were interviewed after completion of the instruction, and all the enactments, both the original unit and the replacement unit, lasted between 8 to 10 weeks. Which schools participated? We had 3 schools. School A is the only middle school in a rural town, about an hour away from here. School B is the only middle school in a suburban town in central Michigan. School C is a charter school also in a rural area. Schools A and C taught the new unit, the transfer-only unit. School B continued using IQUIST. So this school was our control in that sense. These are the number of kids that participate inside there. I don't know if it's, altogether we had between close to 400 kids in the study. The exact numbers are not important right now. Out of about the 400 students, 71 were interviewed, 42 from the systems transfer approach, and 29 from IQUIST. We chose them to try and represent as a broad range of students' abilities. However, even though we tried to do that, the students in both interview groups, when you looked at their post-tests, they scored on average a bit higher than the average kid. So they're not really representative, they're a bit better. That's typically the case when you ask a kid to volunteer to talk. These tend to be not your run-of-the-mill kids, but the effect size is small, so it's not really a big thing that's going on over here. But what's more important is that when we compared the posted scores of the kids being interviewed from one group with the other group, there was no significant difference. So we can use the interviews to compare between the approaches. So we cannot generalize from the kids easily to their entire group that they were studying in, but we can compare between them. The teachers. At school one, we had 2 teachers. One was a very experienced teacher, 26 years of experience. Everybody wants their kid to study in this class. Okay, good teacher. Okay, the other one was more junior, 6 years of experience, still learning how to become an excellent teacher. Both had taught the units twice before the study, so they were pilot teachers as well. We piloted the unit for 2 years before we actually did the full study. So they both were very well acquainted with the unit. In School B, which is the school that continued teaching IQuest, 2 teachers again, one with 14 years experience teaching science, the other was 16 years, of which 9 were in elementary school literacy, and 7 were in science. They're both very good teachers. The first one, also an outstanding teacher, graduate of MSU's graduate program, really a good student, a really good teacher. And for them, this was the second year they taught the IQuest unit. The school had adopted the curriculum the year before we started the project. School C was a completely different situation. We had an outstanding teacher there who at the last moment changed jobs and moved to another school, and they didn't have anybody, so they took an elementary school teacher who had been a teacher for 12 years, 8 in science. They moved her up into 7th grade. Okay? Her science was not very strong, but she was an amazing teacher, an amazing pedagogue. She knew how kids work and how to get them to think and how to get them engaged. Okay? It was incredible. We had a researcher present in her class twice a week giving her feedback at the end of the lesson. The following session, not the following day, the following session, she was already doing what we said. I mean, her learning curve was incredible, absolutely amazing. So although she started off in a completely different place, results will show that she actually did the best in the end of all the teachers. And all the teachers were given PD prior to the units, okay, on the unit and on 3-dimensional instruction in general. Okay. As I said, we had pre and post tests. How much time do I have?
You can go another 15 minutes.
15, okay, that's fine. I just want to be sure. Okay, we had a pre and post test. We identify the elementary and middle school Ps, and according to them, in physical science, and we developed items for them using the evidence center procedure, which I think many of you probably know from Joe's other projects over here. Altogether, we developed 32 items. Each item was cognitively pre-tested and then revised to make sure that the kids understood the questions as we understood them, and that we were understanding their answers as they intended it to be understood. We were very careful to develop the items so that their language did not bias between the 2 approaches. So we never asked for a form of energy. We never talked transfer. And so we just had phenomena, and we asked them to explain a phenomena or draw a model for phenomena or something of that sort. But we left it open completely what language they could use in their answers. In the pilot years, we tested these tests. We discarded all that did not behave psychometrically well. We ended up having 7 items in our pre-test and 10 items in our post-test, in which the same 7 items were both in post-test, but we added on 3 more middle school. And of the 7 pre-test items, if I remember, 3 or 4 were elementary school items. I think 3 were elementary school items and 4 were middle school items. We developed a rubric for every item. Now, since this is a big issue, since we wanted to study their ability to use 3-dimensional knowledge, our rubrics had to look at their ability to integrate the 3 dimensions. We did not want to study each dimension separately. So we developed rubrics that the score increases as the kids are able to better integrate across the various dimensions. This was a very, very challenging thing for us to figure out how to develop these rubrics. There's still definitely place to improve upon them. I've yet to see a really good example of how to develop 3-dimensional rubrics. Okay, so this is our attempt. This is an example of a rubric for a question. It's a modeling question, so there are 2 aspects to the process. One is specify the components or the variables. The other one is talking about the relationships between the different variables. So these rows are our practices, and this increases, the score increases as the kids are better able to integrate between the practice and the DCI and the cross-cutting concept. Now it's built so that if a kid ended up, let's say, over here in this row, he could not score higher than that on the second row. You couldn't get more on a relationship if you didn't succeed in identifying, okay, the components properly. Again, pluses and minuses, there's still work to be here, but this is not the focus of my talk right now. So I'm just presenting this over here. We can talk about it more afterwards if you want to.
David, were those cumulative?
Were they?
So for that first row, scores were 0, 1, or 2. Did
Yes.
you get an additional 0 or
Yes.
2 for the second row?
Right, yes, yes. In the interviews, the kids were shown 5 short videos, when I say short, 10 seconds long, each video, of different phenomena, and asked, how can you use scientific ideas to explain why whatever they saw, okay, moves like it does. So they're neutral, again, we can use them in both approaches. We did not prompt for them to use energy ideas, because one of the things we want to see, are they going to use energy? Yes, it makes sense, we just finished teaching them energy and they know who we are and so on, but still, we want to see if they spontaneously use upon it or we have to actually prompt them to use energy. After their initial responses, non-instructional prompts were used to clarify ambiguous student statements. The prompts try to use the student's language as much as possible. For example, if a student said, the ball loses energy, the interviewer might ask, what do you mean it loses energy? So we try to parrot the language that they're using just to give them back their question. Can you describe this a little more? The 5 phenomena that we used were a rolling golf ball coming to a stop on sand, bread baking in a solar oven, an electric motor being turned on, spinning, and then being turned off, a cart oscillating between springs until it stopped, okay, and a ball being released and falling. The phenomena cover a broad range of processes and they can be interpreted at different levels of detail. So for example, with the cart oscillating, a kid can focus on the oscillating and not talk about the dampening of the motion, or they can choose. So the phenomenon is rich enough so the kid can choose what they're going to focus on, or they can talk about many different aspects. We chose the falling ball because you wanted one phenomenon that would give the kids who had studied this, the systems transfer approach to see if they would invoke fields themselves inside there. The tests were scored by 6 experienced teachers who did not participate in our study. We simply hired them, we trained them, okay, how to use the scoring rubrics, okay, and they scored all the questions. The tests were all mixed up, pre, post, IQuest system transfer. So when a teacher got a test, they had no idea what they were looking at. And the interreliability for each one of the items was at least 80%. We then used polytomous Rasch techniques to calculate item difficulties and student abilities. Does anybody not know what this is? Don't be ashamed. Rather than just adding up scores to grade on each item to create a final score, how well you did in the test, Rasch is a process will take into consideration how difficult an item is and how much that will contribute. So a more difficult item will in the end contribute more to defining your score and so on. Now, how do you know if an item is difficult or not? If kids succeed in answering a certain item relatively well, that item must be relatively easier than a different item which kids did not score as well. That's putting it very, very, very general. But so in the end, we get out ability scores, which are equivalent to just adding up how much they got on each thing, but it's a weighted score. But it also lets us know, gives us information about the difficulty of the different items. We did this for each approach separately. And then we compare the item difficulties between the two approaches. Now, if the items behave similarly in both approaches, we can say that the test is not biasing against one's group. So we want to see that the items are performing similarly across both groups. I'm not talking about the scores the kids get, but the difficulties of the items. So the items can have equal difficulty, but still one group scores much poorer than the other one. So this is the first thing we did in order to see if we could actually use the same test across both groups. And the results were yes. The items, performed similarly enough so that we could use it to compare between things. And for those who know a bit about Rasch, the infinite outfit of all the items was excellent. The borders are typically allowable borders are between 0.75 and 1.33. That's the traditional limits. This is a Wright map, and what you see here are the pre and post scores of everybody put together. Both approaches, we're not distinguishing between them. You see the dark gray is the pre, light gray is the post. We see two curves. We can see a shift to the right, so overall kids learned. These are item difficulties. Now, again, I'm not going to go into this too much, but each row over here is an item, and you can get different scores in an item. You can get 0 points, 1 point, 2 point, 3 point. And so the difficulty of getting 2 points is greater than the difficulty of getting 1 point. So 2 points is going to be further more in this direction. So this map shows us you basically both the distribution of the skills of the students, their abilities, and the item difficulties. Why this is important, we can see that almost all the items are to the left of this point, to the right of this point, which means that the items were relatively difficult. We did not have enough easy items. You basically want to have items covering the entire range of abilities. We do not have enough at the low range in this test. What are the results, basically? The IQUIS kids started with stronger preschool, with pre-instructional knowledge. They are from the suburban school. The other ones were rural schools. They started off in a better place than the other kids. However, when we compare the post-test and we use propensity score matching, does people know what propensity score matching is? Basically, you use some information to try and make pairs between the kids in the two approaches, and then you do a paired t-test rather than independent pair t-test. It's a much more powerful method of comparing. The problem is that it reduces your sample size because there are certain kids that you cannot pair with other kids, and so it decreases your sample. But if you end up with a large enough sample size, it's a much, much stronger method of comparing between two approaches. So we use propensity score matching, and what we found, in spite of the IQUIS kids starting off stronger, that the systems transfer kids did clearly better. Not only did they be better, we look at, so this is the systems transfer approach, and these are the IQUIS kids. What we did then is we divided each group into 3 subgroups. Kids who pre-scores were at the bottom quartile, the middle 2 quartiles, and the top quartile. And then we compared across them. So this allows us to see how well the 2 different approaches support kids who are weaker, kids who are in the middle, kids who are stronger. And we saw that regardless of which quartile you belong to, the system transfer approach was better for you. So kids who began off weaker, system transfer approach was stronger. Kids who were doing well to begin with, system transfer approach is stronger, and also in the middle. So the new approach seemed to be more beneficial for all kids regardless of where they were on the spectrum. Our analysis, we did it 5 more minutes. I hope I get that, yeah. Okay. We did a qualitative content analysis of the interviews using categories that we drew from the literature. So we were looking for how they use terms in their talk. So how do they talk? Do they talk about transfer? Do they talk about kinetic energy? Do they talk about speed? So we used key ideas that we expected them to use based upon the literature. And then after we did this, we start looking which ideas did they use in conjunction with each other? Which connections are they making? So like the idea of integrated knowledge is that you're able to connect different ideas. So then we looked at, after we had seen which ideas they raise, which ideas do they connect? And we built a map that shows how often kids connect different ideas. And we could build maps like that for each student per phenomena. We could average across phenomena. We could average across kids in the 2 different approaches, which is what you're going to see here, but I want to go back to here once. Over here, these are the primary concepts that kids raised while talking and how often they were used when they were talking about it. Black is IQuest, cross is systems transfer. We see that the IQuest kids talk a lot about forms, which is to be expected. That's what they learned, okay? What is surprising, they talk a bit more about transfer than they do about transformation, okay? They almost never talked about dissipation, and when they did talk about conservation, they talked about it mistakenly. They made mistakes. The system transfer kids, they barely mention forms at all. It's not part of the language. They talk all the time about transfer. They don't mention transformation at all, okay? They do talk about dissipation, and they didn't mention conservation. Now the maps. What do these maps show? Again, these are the key ideas that the kids mentioned. The bigger a circle, the more often that idea was raised. Then the lines show which ideas were connected with one another. The thicker the line, the more that connection was made. What we see when we look over here, these are the IQuest kids, we can see that there are about 5 ideas which are the ones that are holding everything together. Okay? We have forms, force, transfer, transformation, and speed. When you zoom out a bit closer, the really big ones that are mentioned here a lot were forms, speed, and transformation. That is, transfer and force were a bit less. When you go to the system transfers kid, the conceptual network is simpler. There are only 3 ideas instead of 5, and actually there's only 2. This one is also much smaller. We have transfer and speed, that's it. That's what's holding everything together. The conceptual model of the kids, what they needed in order to answer these phenomena was much, much simpler than the other one. This, I think, is the main reason why they outperformed the other ones. Okay? It's more of an expert-like model. An expert, we've learned, the conceptual models are based upon the key ideas. Okay? They're very parsimonious, based upon the key ideas of the discipline. If you have many, many things going on in your head, it's much harder to decide, okay, what's appropriate here? What am I going to use? What am I not going to use? If you have a very simple parsimonious model, that's the only thing you have. That's what you use. And if that thing works, you'll succeed. So, what is here that I didn't say? Nothing that I haven't mentioned before, I think. So as I said, these system transfer kids outperformed the IQuest kids in just about every aspect, quantitative aspect. That is not only in their total scores on the test. When we look at each item individually, in the post-test there were 10 items. 9 out of the 10 items, the system transfer kids did better than the IQuest kids, and on the 10th item there was no significant difference between them. We said system transfer kids developed more parsimonious knowledge networks in relation to energy, which is more like an expert's conceptual network. Okay? The process of analyzing phenomena in the system transfer approach appears to be simpler. Okay? When you look at a phenomenon, you don't have to start thinking, okay, which types of energy? Is there transformation going on, or is there transfer going on? Okay? You don't have that. We don't have types of energy. We have energy. You have to think at what processes are going on. Okay? Identify systems, processes, and then who's transferring energy to another. That's what you have to do. The same three things every time. And finally, the inclusion of fields did not appear to be a significant barrier for the kids. And again, this is looking only at macroscopic phenomena. In our second pilot year, we included also chemical phenomena, and we ran up against the wall over there. I don't know if it's a problem with this approach or just a problem with middle school kids. They may not be ready to go there yet. I don't know. Okay? But if you remain in physical phenomena, physical macroscopic phenomena, I'm coming away learning that this approach seems to be preferable over the traditional way of teaching energy. That's it. Thank you.
Open things up for questions.
Yes, Xiaoming. Yeah.
Hi, Gary. First, thanks so much for your talk.
Thank you.
And I really appreciate your creative approach to represent the model of conserving energy. And also, I appreciate very much that your instruction approach, your focus on the transformation rather than the form of energy, which reminded me that when I was in China, there is a very famous Chinese teacher who taught middle school energy. Also, because traditionally people will begin with the formal energy, but that teacher actually began with the transformation of energy.
Okay.
And that is really different and amazing, and I use that video in my PD actually.
Okay.
So my question here is, traditionally when we talk about the transformation of energy, there's a very important concept is work. So actually the work explains why energy transform from here to another or transform. I'm not sure how this new approach include or incorporate the work in the instruction.
It doesn't. Work is not mentioned in this unit. And in many ways, talking about work it becomes a circular argument. Also, you define work as a change of energy. There have been studies showing, again, I didn't show them all, that traditionally, even before the forms-based instruction, the way kids were traditionally introduced to energy was talking about work, okay, force over distance, and then we start talking about, okay, the energies and so on. And research has shown that that does not seem to help kids, okay? When we interviewed more advanced students, including university students and professors and so on, and lay people also, and we asked them, this is a different study, okay? We asked them to explain things. The word work was not used. Even physicists, they don't talk about work, okay? It's not something that they use regularly. They talk about changes in energy and flows and all kinds of stuff, and Gibbs and enthalpy, and you name it. They don't talk about work. It doesn't seem to be something that they use regularly. And I'm not saying there are not situations this is not the appropriate way to think, but at least in the situations that we gave them, work was not mentioned by them. So why make it a part of our instruction? If they can get to it later when they have to study quantitative, and then perhaps work does become more important. Yes, Melanie.
So, but I think what experts would involve is forces.
Yes.
And I wonder about this approach separating out energy and forces. And I know we talked about this before, but this idea of trying to get students to explain why the ball falls in terms of energy is a very difficult conceptual idea, as opposed to the ball falls because of
Right.
there's a force, there's an attractive force. So I just was wondering.
Okay.
something about that.
Another interesting we found out in the interviews we did with experts is that when they are asked to explain a phenomenon that lies outside of their realm of expertise, they fall back upon forces. Okay, forces is something that's more intuitive, okay, than energy when you're not dealing in a situation that is familiar to you. There are a couple of limitations to what we did over here. First of all, we decided that it has to plug into IQuest. Okay? In IQuest, forces are taught in 8th grade, not in 7th grade. They come afterwards. One of the reasons we did that in IQuest way back is because we thought that maybe one of the reasons that kids tend to fall back upon force-based explanations rather than energy-based explanations is because they began from forces. That is something that's intuitive, that's something they learn, and energy is just another layer on top of that. And they continuously confuse between energy and force. They talk about energy as if it's a force. So one of the ideas in iQuest was, that perhaps if we switched the order and we taught about energy before forces, we might help see the value of energy. We never studied that. I don't know if it actually happens. There was something else I wanted to say. And also, while all the disciplines need energy, chemistry, biology, they all want energy, so in the curricular sequence, they all want energy to be taught very near the beginning of the sequence so they can build upon that. Nobody uses forces, okay, except chemistry to some degree, and physics. Biology and earth scientists, that's not one of their main tools. Okay, the idea of forces. Yes, it's there, but not, Newton's laws and all those kind of things that you always teach about forces. So that was also helped us make the decision to move force more towards the end of the sequence and keep energy up front. The force unit in IQuest does attempt to formalize the connection between the two. So it's not just forces, it's really a force and energy unit. It tries to bring the two together. We do mention forces a bit over here because when we're talking about magnetic fields and the interaction, so forces are there. We do talk, and we saw in the conceptual networks that force is one of the ideas that the kids mentioned, but we don't teach anything about the nature of forces. We just draw upon their intuitive understanding that if you can feel it's pushing it, there's a force going on there. Yes, Bob.
So I got two. One's a methodological question and the other one's theoretical. First, the methodological one. To what extent did the iQuest teachers receive the same kinds of resourcing and support that you were providing to the ST teachers? In other words, did they get the same kind of professional development, same kind of contact from the researchers and those kinds of things?
Same thing. As I said, this was the second year they taught iQuest. We were with them the first year and the second year we were providing them with PD, just as we provided everybody else. We were available on call if they had questions. When I came visiting, I used to go say hello and give them some feedback on their teaching. So in that sense, they got the same support as the teachers in school A. Teacher in school C got a different level of support because she did not understand what to do. And so Izzy, who's not here, Izzy was, sorry, you're invisible, okay? He was there twice a week, all the time, okay, helping her. And he can say that she's an incredible learner, okay? Really incredible. You don't see things like that very often.
She goes from, she teaches one class and then she tells them. And I kind of go after the class and I say, you can just next time, try to let them kind of work towards it. It immediately happens. Like 7 minutes after she starts her next section, and she's a different teacher. She stops telling them and she lets them figure it out. And I'm just sitting there with my camera going,
Okay. She's a very warm, engaging, motherly type of figure. The kids felt very comfortable in arguing and expressing themselves. It was a great class, her classes, okay? So although she did not have the content knowledge, she did not know middle school stuff, everything else, she was completely on top of it.
So my theoretical kind of question here is, one of the issues that, you know, all of physics and physics education deals with is that we physicists keep teaching things the way that these concepts developed historically, right? So forms of energy is how we kind of came to understanding of energy gradually by realizing all of these things are interconnected, and it's kind of useless as a concept for describing the way we actually think about things. This approach seems, you know, way farther along the lines to what our modern physics understanding of these things is. But my question for you is, why didn't you take it the next step and base it on conservation?
Quantum.
Well, that's all right.
I was waiting for it.
That was coming too, right? So two pieces. One is that, you know, in the physics understanding, energy is simply this underlying quantity that exists in a system that remains invariant, right? So as long as you draw the system boundaries, you just have this invariance, and if you see more over here, there's got to be less over here. That changes the story a little bit, right? But also gives them that kind of richer conceptual understanding. The second one is with respect to fields, right? In that, you know, why not introduce exchange of virtual particles? Because in some ways, right?
That's what's going on. That's what's going on. I'll begin with the second one. Okay. Forget it. Okay, they'll have to wait till they do their master's degree in physics to get to there. Okay. Regarding conservation, I think we do deal with conservation, but until you look at numbers, okay, until you cannot actually you can never demonstrate conservation. Whenever you do an actual experiment, and you know, you don't measure energy, you measure other things, you calculate energy, and there's never energy conservation. Okay, what we have done, something nice we've done with Knut, who has a master craftsman in his lab, we have a pendulum that we can slowly make the pendulum more and more frictionless. And so they see that you can develop a graph of energy that it asymptotically reaches a certain point that you said, okay, at that level there should be conservation. That's the closest thing I've seen as an instructional method of really showing that there is conservation. Conservation is not a middle school requirement. Let's be that. It's not. Conservation is not one of the NGSS middle school expectations, and there are so many other ones that we're not dealing with. Why add on one, which is not there, but is there in high school? Okay, I'm not so sure if it's a drawback to leave it qualitative, so that you have the idea of energy moving from one place to another, and the fact that you know it always has to be in some system. Why would you think that something is lost? Okay, or that it's not the same amount. But leaving it qualitative at this stage, at high school, assuming we get the new grant, to take it quantitative and actually look at focus on the idea of conservation. That's my guess. That it would be rushing it. There's no big advantage, I think, in doing it at this stage. Andy?
So you don't talk about forces, but you do talk about fields.
Yeah.
And so my understanding is that IQuest does not talk about fields.
Right, it does not.
So you're comparing a version that talks about fields but not forms with a version that talks about forms but not fields.
Yes, that's very correct. That's very accurate.
So, you know,
one F gets replaced with another F.
Fields is a powerful idea that middle school students are ready to understand for some phenomena. And if so, fields can be more useful than forms of energy for those phenomena.
For certain phenomena, yes. As I said, for macroscopic phenomena, right. Yes. Yes, I think that is what we're saying at the end. I remember being at a conference with Ramon Lopez, who was one of the people who's pushed to include fields. And there were a whole bunch of teachers saying, we can't teach fields. And his answer was, how do you know not? Okay, well, how do you know until we try it that it really, really doesn't work? And one of the things we did, we looked at all the research literature that we could find about teaching kids fields, and everything that we found was that they don't get it, but everything focused on mathematical representations of fields, and not trying to teach that a field, it's something real, it's really there, it's an object in that sense, it's a system, okay? It can change, okay? You can see it if you use the proper things, okay? Which is very different than any way we could find that was taught in the past. And yes, it seems that that representation is something funny to say, more physical. They can see it, they can feel it when they squish two magnets together. They can accept that it's reality more than forms of energy. So what's the difference? You know, what makes something one form and another form, and so on. So yes, I think.
Okay, so I can totally buy that part of your conclusion.
Yeah.
But there's another implied conclusion about the uselessness of forms
Okay.
that I'm much more skeptical
Okay.
of. Partly, I think even the phenomena that you're using, when you're using heat and motion as two different visible indicators of energy,
Mm-hmm.
you're not calling them forms anymore, but you're still kind of saying, we got these two things. And I know when we move to biological systems, it's like living organisms organized around the search and the use of chemical energy.
Okay.
And
Yeah.
how you can kind of say how you can avoid chemical energy as a form for kids who do not have an atomic molecular understanding of systems. I'm skeptical.
Okay. First of all, if I said useless, I want to take that back. It's not useless. It's shorthand. I think it's something that can be layered on a deeper understanding if you understand the systems transfer approach, if you understand, okay, what is going on at the field, at the molecular level, then it becomes shorthand. Rather than talking about rearrangement of atoms to energy transfer, you can say, okay, chemical energy is being transformed, okay? But it in itself, to begin with, I think it doesn't lead to understanding. It can allow you to say what you want to say shorter. Now, another thing is that,
So I don't agree.
okay. Well, when we talk, the thing is also, chemical energy is only relevant when it changes. If there's no change in chemical energy, no chemical reaction going, why talk about it? Heat, you talked about heat or thermal energy, it's only of interest if there's a change to it. If a system remains kinetic energy, if the system remains at constant speed, I don't care about the kinetic energy, it's not important. What we're only interested about are processes that lead to changes in energy. The new approach helps you focus on that. The old approach, it has temperature, so should I include thermal energy? The fact that its temperature is not changing, okay, but it has a temperature, so should I include that? It's happening, I'm doing an experiment at this height. Should I consider gravitational energy even though it's happening at a constant height? The system transfer approach, because you start by focusing on which processes are going on, it can help you identify which forms of energy are relevant. That's what's important, okay? Not just talking about the thing has heat. That means nothing to me if the temperature is not changing. So again, I think there are situations, and especially, I want to take it one step further. When you go out and you read popular mechanics or a newspaper or whatever, that's another study that we did, by the way. We did an analysis of the media, of how the way they talk about energy. Okay, they definitely don't use the system transfer approach of talking about energy. Okay, this is something new. So kids have to be able to speak that language if you want them to be scientifically literate. That's what's out there. So that's another reason why, yes, forms are still important. That doesn't mean that in 20 years, when we have a whole generation of kids who may have been educated by this approach, will still be important then. Maybe we'll see a change in the vocabulary being used. But presently, I agree, it still is important.
So there's two things I want to argue with. One, the notion that forms is sort of a shorthand after you've learned about fields and trends.
Okay.
I'd say forms is also a transitional way of making sense of the world for kids who are not prepared to understand fields and transfer, especially at the molecular scale. And so the question,
Okay.
you've got middle school kids. They're kind of shaky on organisms being made up of cells, and they're even shakier on cells being made up of molecules and molecules being made up of atoms.
Mm-hmm.
So the move to say, well, we'll just take all this down to the atomic molecular
Okay.
scale and then everything follows, well, it's theoretically true. It's not a useful thing to know
Okay.
for middle school kids.
You're right. You're right. Certain processes cannot be at that level age be taken down. But on the other hand, the evidence that I know shows that just leaving it at the level of talking about chemical energy they don't understand. In other words, the evidence I've seen, okay, that by remaining at the level of labeling things, it doesn't give them anything, really.
Which I totally agree with, but I'm still saying as a transitional, at the front end is transitional and not just a
Okay.
conclusion at the back end.
Okay, so yeah,
The other thing I want to mention is I think certainly in the case of chemical energy, when it's not changing, is still extremely relevant. Like, why do we put on fat?
what do we put on?
Why do we put on fat? Why do we gain weight? Why do penguins store up a whole bunch of fat before they go and lay their eggs and so forth?
Mm-hmm.
They're storing chemical energy, and then nothing's happening to it right now.
I would argue they're not storing chemical energy because without the oxygen, there's nothing to do there, and they're not storing oxygen. The fat itself has no energy. It's only when it reacts with oxygen, okay, that you can talk about the energy of the fat, and they're not storing oxygen. So what are they storing? They're storing mass. They're not storing energy.
I don't think that's a particularly useful way to think about what organisms are doing when they store food, some form of food in a form that's going to be useful later.
But that
I
exactly
agree that the energy can be, and of course, the penguins and everything else is living in an oxygen-rich atmosphere, and so in some ways, storing energy is shorthand for storing materials that are going to be able to react with the oxygen and release energy. But there are ways of identifying those materials, and it's certainly very, very useful to understand that plants and animals and microorganisms are all organizing their lives around trying to obtain and keep these kinds of materials and use them when they need them.
This can go on. The picture that you're painting right now, yes, I think it's something that kids can understand at middle school. However, I think it creates misconceptions that are very difficult to get rid of afterwards. And those are one of the reasons why kids, when they move on, aren't able to see the connection between energy in physical environments and energy in life science. You're talking about two different things, okay? You're using the same word, but the way you're dealing with them is very differently. And kids so far have not been successful in bridging that gap, okay? Now, I don't know if it's realistic to expect kids in middle school to be able to leap across. I don't know. It's probably too early to do that. It's a high school thing. And the question is, if at high school, if kids are not ready at that stage to go down to the molecular level and to look at the fields, what's happening in chemical reactions and so on. That's one of the things we want to find out. It may be that it's best to leave these issues relatively untouched at middle school rather than creating certain misconceptions that afterwards we have to struggle against. I don't know. That's an empirical question.
Other folks want to jump in on this, or have other questions?
Yeah. Oh,
I don't think we know the answer here.
right. I don't.
I think you clearly have found out that it's very difficult to deal with molecular level systems.
In middle school.
using
Yeah,
administrators
absolutely.
in this
Yep.
approach. It's not clear when this approach will bear fruit, right? Because I think it's been severely underestimated how difficult it is to apply some of these things at the molecular level, because of all the backfilling and underpinning that has to go on. And I think, so I don't think we know the answer. So we have to have some way of being able to help students build on what they know in middle school. And I have no idea how to do that. But I'm just gonna say that we have, I think we've severely underestimated
The
how
difficulty.
difficult,
I agree.
dealing with the unseen
Mhm.
level
Sure.
when we try to deal at the level of that.
Sure, sure. I remember when I realized that for any chemical reaction to occur, there has to be a third system involved that will take away excess energy.
There you go.
Okay,
Yeah, that's right.
that blew me away when I finally realized that. Okay, you cannot, and suddenly I realized why I was having difficulty understanding the energetic aspect of chemical reactions. Why don't they bounce back into where they were before?
Well, they do.
And and these are things that middle school kids are clearly not ready to deal with
Right,
them.
and probably
Clearly
not
not.
high school.
Probably, maybe.
So can I have one more question?
Sure, go for
So in the framework, you say you don't give any kinds of energy any name, but in the framework, it clearly says there are two kinds of energy.
Right, kinetic and
potential.
potential. Right.
So what made you do away with that as well?
The systems transfer approach does not need potential energy. Okay, for it to work. Okay, potential is energy of fields, which is just another system. And if we wanted to focus on the unitary nature of energy, okay, by introducing both potential and kinetic, forces us again to deal with the idea of transformation. What is different about the energy in fields rather than the energy in objects? Okay, actually, going back to quantum mechanics, we know that everything is fields. There are no objects. Particles are actually fields. But that okay, but that'd be a bit crazy to go there. And we thought that actually bringing in potential energy was making things more complicated. Wow, that was long.
I'll observe there's some really interesting disciplinary differences here, right? Because my reaction to Andy's notion that the macroscopic shorthand is conceptually necessary as a physicist was immediate aversion, right? I don't think we need to teach pressure as an independent thing in order for kids to understand at a molecular level the conceptual nature of pressure. And then he gave the example from the life sciences, and I'm like,
Yeah, there is something.
totally, right, there's no way to
It is-
understand food webs and those.
Yeah, there is something there, absolutely.
Yeah,
Without that
kids
piece.
kids already have lots of ideas about energy and living systems. They say, I got a good night's sleep last night, so I'm drinking Red Bull, and that's gonna give me energy.
I know,
So-
It
I know.
says 5-hour energy.
Those ideas about energy don't exist in kids' heads.
Of course they're there. Of course they're there.
And it's not like you can avoid them when you're teaching middle school life science.
Absolutely.
And then the chemists are just hopeless because the energy's all down there, those little things. Thank you, everybody, for
Thank you for coming.
attending. David will be around Create for the next little bit, so everybody wants to talk to him, you're welcome to continue yelling at him and arguing with him on these things.
No. It reminds me of our lunches upstairs. There's sandwiches we used to.
Why haven't you been there?
Andy, thanks for coming. It's like old times, like old times.
So, you're sort of sneaking in and not even letting people know that you're here.
I came here to gather data. I was really not planning on being here, And there just simply were so many snow days, weather days. It's been nuts. I've been here for 2 weeks and I've only been in school twice. It's been crazy. So I said better not let people know I'm here so I can go to the schools in the end. That's what happened.
Well, if you can make it upstairs,
I will
there's
do.
usually people around.
Same spot, huh?
Uh-huh. We'll see you.
Take care. Thanks. Bye-bye.
Thank you. Thank you.
Thank you.
I can see the approach actually was developed mainly based on physics.
Yes.
So that I can imagine that curriculum will be very appropriate in China because we use separate. Separate. Curriculum. Yeah.
We have to get moving because there's another group coming in after us. That's your speaker gift.
I don't need it. Come on.
Well, look at it first.
Who did I give this
and then
to?
you can give it back.
The camera's gone. Oh, the camera's still
The
there.
camera's still there. You can leave it with the camera.
So let me get myself out of here because someone else is coming
Yes.
too.
We do have another group coming down right away, so we do need to move out. It's all about exchange of virtual particles.
I know what I realized at the end.
I said it's all about exchange of virtual particles.
Isn't everything? Yeah, was good talk.
Yeah.
Huh?
Good. Yes, very good.
Think so?
I didn't have all the, I didn't know what some of your stuff was more recently. So
But it was I skipped over certain things like, no, what's Raschman, what's,
that was good. No, that was the right thing to do because it made it more conceptual, but it gave them a sense for how the research went, which is really what we want to do because some of these folks need the research time. Sorry, folks, there's usually a downtime in between.
Hey, great to see you.
You're lovely. I'm taking your valuable kind of class.
No, the Tiki Factory.
How boring.
So we
Oh
don't
my
care
God.
about that.
All right. I have your lavalier and your computer.
Everything.
No, don't take that. Don't.
One more year.
Don't. I've got your computer. You've got.
It looked the same.
That's why I got to put stickers on it. Okay, good.
So we just leave this thing up here? Or
Yeah, we'll take care of that.
well, we should leave this here also so the guy doesn't freak out that it's disappeared or something like that.
There's your computer.
Thanks.
There, you can look and decide if you want it. If not, you can give it back. We'll use it for the next one. There you go.